Okay, so the second part of the polysaccharides that we're going to look at it for today will be the cellulose. And we have learned a little bit about the cellulose, which we know that cellulose is a quite strong and rigid molecule. Okay, where we can get them? Where you can get them in plant cell wall. So don't just write cell wall, because you have to know that cell wall, we can have the bacterioglycan cell wall for the bacteria, we can have the chitin cell wall for the fungus. So for plants, we use cellulose. And cellulose, unbranched polymer. So unbranched polymer, you should know that how we join them. It must be 1,4 glycosidic bonds. But compared to the amylose, cellulose compared to amylose we use alpha glucose, but cellulose, the plant use beta glucose. Okay. In order to form this cellulose molecule, okay, to form cellulose molecule, alternate glucose molecule must be upside down. They have to rotate upside down, or we say rotate 180 degree upside down in order to form this glycosidic bond. Okay, so we're going to join them by using a alpha 1,4 glycosidic bonds. Okay, let me highlight for you. Okay. In order to form this bond, sorry, not alpha, it's a beta, 1,4 glycosidic bond. So let me highlight for you. And then let us draw this structure out, how we can form the cellulose molecule. Okay, I'm going to use 4 beta glucose to draw this, 4 beta glucose. Then you can copy it down in the activity 3.10 here. So first of all, let us look at how beta glucose look like. Okay, so let me draw beta glucose. So as usual, the structure will be the hexagon ring, and then we draw the pillow. So carbon number 6 is outside ring, CH2OH, H, H, OH, OH, H, H, OH, and because it's beta glucose, so OH above the ring. Correct or not? Okay, so why beta glucose? OH above the ring of the carbon number 1. So this is carbon number 1, carbon number 2, carbon number 3, 4, 5, and carbon number 6, always outside the ring. Okay, clear? Can So if you place 2 beta glucose together, let us look at it. If you place 2, okay, beta glucose. So I've placed the second beta glucose. Three. Okay, so beta glucose, OH above the ring at carbon number 1. Can you see that? So this is carbon number 1, carbon number 2, carbon number 3, 4, 5, and 6. So in order to form the bond, it must be 2 OH group together. So it means that either one of them must rotate or flip, because you can see that currently. Let me show you. Okay, where's my pointer? Okay, can you see that? OH group below the ring, OH group above the ring. So if you want to form a bond, you have to rotate, okay? Either rotate the first one or you rotate the second one. So that every alternate, you have to rotate it, okay? 180 degree upside down. So I'm going to rotate it and then change, okay? Can you see that? I rotate it. And then can you see that OH and OH now above the rings? Correct or not? Okay, so let me change the label and change this CH2OH. Can you see that? So CH2OH. Okay, so again, I label this carbon number 1, carbon number 2, carbon number 3, carbon number 4, 5, and 6. Can you see that? You can flip it. So if you compare now, carbon number 6 here is above the ring. When you rotate, it becomes below the ring. Can you see that? Okay. So why we rotate is not like rotate at the same spot, because we rotate. Can you see that the O at the back? Okay. So if you can see my sorry, let me on my camera. Let me show you how the thing actually happened. Okay. Just stop recording a while. So with these rotations, now can you see that OH group of carbon number 1 is still remain at the first, above the ring. And then you can see that the OH group of carbon number 4 now also above the ring. So we can actually form the glycosidic bond. Can I see that? Oops, let me draw it this way. So this one you can write it as a remove SH2O crayons. Okay, one donate OH, one donate H to form the glycosidic bond. Okay, so this is the first beta, second beta. Okay, both of them beta. Then the third one, do I need to flip? The third one actually do not need, because the third one you can see that the OH group below the ring. Okay, so only the alternates, every alternate glucose molecules or beta glucose you need to rotate. So the third one no needs. Okay. So learn how to draw, okay? I received quite a number of times students texted me, do we need to remember the glucose, how to draw? The answer is yes, okay? So carbon number 1, OH group above the ring. So HOH, OH, HOH, HCH2OH, okay? So you can see that it's carbon number 1, carbon number 2, carbon number 3, carbon number 4, 5, and 6. Now you can see that one have OH, another one have H. So down this one again, remove as H2O. Okay, so I'll show you. So only alternate. Are you clear? Only alternate. So if in this case, the fourth one, if I put the fourth beta glucose, you need to flip it, okay, upside down. Okay, so through the condensation process, so what I'm going to get here, now you can join them together already. So first one, you don't need to flip it. So OH, H, CH2OH, H, OH, H, H, OH. And then this one, be careful, H below the ring, then you form the glycosidic bond. Okay. Can you see that? So now this one H. So this one OH, H, OH, H, 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 CH2, OH. Can you see that? Okay. Next one. So third one, no need to flip. H, so form the bond. So you can see that, okay, how do you recognize the structure? Okay. So plus 2 molecule of water. Are you clear? 2 molecule of water. So how you actually recognize this is a beta glucose and how you recognize the cellulose? So first you can see that formations of the bond. Can you see that? Above the ring, below the ring, then continue above, below, above, and then can you see that at the back of the ring, in front of the ring, and then back of the ring? Okay, so how we label this bond? So again, can you see that if I put it here, I remove. So this is COC. Can you see that? So COC, this is a glycosidic bond, right? Okay, we know that it's a glycosidic bond. So, and because they form by beta, join at, this is carbon number 1, okay, number 2, number 3, number 4, 5, and 6. Here, this 1, number 2, number 3, number 4, number 5, and number 6. So therefore, involve carbon number 1 and carbon number 4. And because of beta, then become beta 1, 4 glycosidic bonds. And because of this beta 1, 4 glycosidic bond, okay, special, first, they are unbranched molecule. And because of the rotation to form this beta 1, 4 glycosidic bond, so cellulose molecule is relatively linear. Are you clear? Now, why linear? Okay, you have to know why linear here. Okay, so the thing here is the linear because when you rotate it, now OH and H no longer together, then you won't form this helical structure. Again, relatively linear, non-helical. As you compare to the amylose, which form a spiral, right? Still remember, because of the intramolecular hydrogen bond. But the intramolecular hydrogen bonds here, if I put it, okay, if I draw it now, then you realize it's something like this. Okay. Now, we do know that hydrogen bonds always form. Okay, between the O and the H. Okay, O delta. Okay, so can you see that? O. Okay, how to put it this? Okay, now OH. Okay, CH2. OH. So hydrogen bonds actually can be formed somewhere here. Can you see that? Because H is delta positive, O is delta negative because of the flip in this case. Okay, but do you realize that this part you have the hydrogen bond, this one you cannot form hydrogen bond. It's not like the amylose molecule, you can continue to form the hydrogen bond and then it makes the molecule flip. But perhaps makes the molecule become spiral. In this case, can you see the hydrogen bond later will be formed within here? So it means one up, one down balance. Can you see that? One up, one down balance, another up and down balance. So it means that you will get this molecule relatively linear. Are you clear? Means that it won't form spiral or helical shape. So if I draw it this way, you can see that again, okay, OH, OH. CH2, okay, OH, oh, sorry, OH. Can you see that? So hydrogen bond can be formed this way. So can you see that a hydrogen bond, H bond, hydrogen bond, one up, one down, balance, cancel out the effect. So that's why molecule won't turn into the spiral shape. Are you clear? So this is how alpha helix, the beta 1, 4, okay, beta 1, 4 glycosidic bonds can actually cause the molecule become relatively linear. Okay, so against the unbranched, so similar to amylose. But in terms of structure, why we make them different? They are relatively linear due to what? Due to beta 1, 4. Okay, because you need to flip the alternate glucose or beta glucose so that you can form these beta 1, 4 glycosidic bonds. Okay. Okay, so we have done for activity 3.10 where you can actually draw a cellulose molecule. Okay, a question will tell you how many glucose molecule you need to draw. So always remember, it's not all. Okay, it's alternate. Every alternate beta glucose we need to flip, okay, or rotate it upside down 180 degrees. Okay. Now, why this cellulose is a strong molecule? Why cellulose is a strong molecule? Because it's not one of them only. Okay, so in order to form a cellulose cell wall, we have many cellulose molecule joined together. Okay, so how we join them together? You can see that 60 to 70 cellulose molecule become tightly cross-linked to form cellulose microfiber. This won't be able to take place in the amylose. Amylose is helical structure, so it won't be able to actually form this microfiber compared to the cellulose. Now, why cellulose can? Because just now we learned about the cellulose molecule because of the beta-1,4 glycosidic bond, making them unbranched, that's one. Second, making them relatively linear. So try to imagine if relatively linear, I can actually put another one at the side, another one at the side, and then link them together. So how we link them? We link them by forming this, what we call the hydrogen bond. So in this case, we have two terms that we have to learn here. One is intermolecular, another one is intramolecular. Inter means between. Intra means within. So look at this diagram now. Look at these diagrams. So it's a part of the cellulose molecule. So this is, if I label them, okay, this is molecule number 1. This is molecule number 2. So they are two different molecules. Are you clear? Because we do know that they are unbranched molecules. So unbranched. So this is what? So continue all the way. Can you imagine? So this is the first cellulose, second, I said first beta glucose, second beta glucose, third beta glucose. So you can see that COOH. Where is COOH? So if you label them, this is C, number 6, OH. Can you see it? CH2OH. CH2, CH2OH. Can you see that? So if you label them now, you can see that this is carbon number 1, this is carbon number 2, carbon number 3, carbon number 4, carbon 5, and then band here, carbon number 6. Okay. Now, what we're going to look at it here, this part a little bit confused, but try to follow. This is one molecule. This is second molecule. So if you want to form the hydrogen bonds between two molecules like this, so we say that it's intermolecular. Why intermolecular? Because between two molecules of cellulose. So how they form intermolecular hydrogen bonds? Okay, so dotted line, red color is intermolecular hydrogen bond. Okay, then I use blue color. Blue color is intramolecular hydrogen bond. Okay, so we'll start with the intermolecular hydrogen bond. So how it form? So look at this, O delta negative, H delta positive. So it can form intermolecular hydrogen bond. Can you see that? Yeah. So one, join together. H and O together. H and O together. Can you see that? So this is how these intermolecular hydrogen bonds can be formed. And we do know that hydrogen bond also can be formed within the molecule, make them actually become relatively linear, one up, one down, right? So how this one up, one down can be formed? Now look at this. H delta, can you see that? H delta negative, O delta positive. So can form intramolecular. And then here intramolecular, and then here intramolecular. So that's why I say that they are relatively linear, because OH, OH, OH. Can you see that? O and H, hydrogen bond, hydrogen bond. So one down, one up, one down, one up. So cancel out the effect. Therefore, cellulose molecule relatively linear. Can you see that? Intramolecular hydrogen bonds can be formed. Okay, so within. And then the red color one is an intermolecular, because between two molecule of cellulose, between two molecule of cellulose. So how many you have? 60 to 70 of these, okay, become tightly cross-linked to form this cellulose microfibril by forming intermolecular hydrogen bonds, because we want to join them together. But in order to form like this, we need to make sure that my molecule is linear, right? If non-linear, you won't be able to pack them nicely. If they are, okay, like for example, they are curved, they are branched, okay, then definitely you won't be able to link them closely. Are you clear? So this is a structure. So due to what? Due to the cause we use beta glucose. And for beta glucose to be linked, then every alternate beta glucose have to rotate, okay, have to rotate 180-degree upside down. Okay. And then also because of this rotation to form the beta-1,4 glycosidic bonds, therefore this molecule, they are relatively linear, and therefore we can pack most of them together and form cellulose microfiber. Okay. So cellulose cell walls, we do learn about this. They are fully permeable. When we use the word fully permeable, we have to continue to both polar and non-polar small molecule, including the small protein, with a size exclusion estimate about 30 to 60 kilodalton. So it's molecular weight for its or molecular mass. Okay, so it's you compare with the plasma membranes. Plasma membrane, they are selectively permeable. Okay, they are selectively permeable because they actually act as a barrier to block or to bar the polar hydrophilic particle to pass through. Okay, then this cellulose microfiber later will held together to form cellulose fiber, again by the intermolecular hydrogen bonds, and therefore they have very high tensile strength and difficult to break and withstand the large turbo pressure. And typically, they have several layers of cellulose fiber running in different directions. I've shown to you guys before. When you have different directions, then when the pressure press on it or exert on it, it won't actually make them slippery, and the molecule will be very, very strong, the structure. So there are some molecules have to cross-link the fiber and form glue-like matrix. So the arrangement of cellulose fiber help to determine the shape of the plant cells. So you look at this, guys, again. So this is one cellulose molecule. Look at this, how I highlight. This is one cellulose molecule, cellulose molecule, cellulose molecule. So 60 to 70 of them, okay, join, okay, linked by the hydrogen bond, therefore forming cellulose microfiber. So this cellulose microfiber, you can see that they run, okay, or fiber, they form the fiber, can you see that? And run in different directions to form the plant cell wall. And because they run in different direction, I draw it is, so it creates the gap. So that's why this gap allow particle to diffuse across, okay, the cell wall. I use the word diffuse. Why diffuse? Because it's not involved the caryoproteins or transport protein at all, right? So therefore, it's a diffusion rather than faceted diffusion. Even water molecule also, we say diffusion, not osmosis, because osmosis require selectively permeable membrane. Okay, so with this, I have done for the first part of today's lesson.